Alrighty, so now I'm trying to recreate the water potential notes that I delivered in class for those of you who either left early or who ended up not coming to class that day. These should go on page 57, and if you need space, 58 of your notebook. And let's go ahead and talk. So water potential is the free energy or the potential to do work of water. Now, when water is floating around, just sitting there with no solutes in it, it's got a lot of potential energy to do work. But the more you add solutes, the less potential energy there's going to be. So let's say that I have some solutes. So here I'm going to have some glucose and I stick it in water. If I stick it in water, and I'm going to go ahead and draw some water molecules. And don't mind the orientation of the water molecules. I do not remember off the top of my head where the partial charges are on a glucose if you draw it as a hexagon. So I'm just drawing kind of water molecules attracting. So these water molecules are kind of held in place by hydrogen bonds to this solute. So the more solute that you have in a solution, the more tied up those water molecules are going to be, and the less potential energy they have to do work. Therefore, the lower their water potential. So now I'm going to draw a couple of other solutes and we're going to see what happens when they dissolve in water. So if we have something like sodium chloride, which is just a sodium and a chloride ion. They are held together by an electrical attraction, but if either of those ions comes across an appropriately charged particle like another ion or water molecules, then those can dissociate or separate. That's what happens to salt when it ends up in water. So it will separate into two ions, like a sodium and a chloride ion. When that happens, each of these ions is going to pick up its own shell of water. And I'm going to go ahead and I'm going to draw that shell of water, just a few water molecules to illustrate. Obviously, there would be more water molecules, but I don't want to take up that much time drawing a bunch of Mickey Mouse heads. So notice that you have two particles that are dissolved in this water, and so then you're going to have more water molecules tied up. So the more ions or particles you form when a solute dissolves in water, the more the water is going to be tied up, not able to have the potential energy to do work, and the lower the water potential is going to be. So let's talk about how this relates to the solutions we've been talking about, hypotonic and hypertonic solutions. When you have more solute added to something, that is going to be a hypertonic solution. When you have less solute added, remember that is a hypotonic solution. Now remember, when you add more solute to a solution, that's going to tie up more of the water molecules and that's going to lower the water potential. So my bad. For a hypertonic solution, you have a lower water potential. And by the way, water potential is represented by the Greek letter psi, and it's an uppercase psi. I remember that because it looks kind of like a trident. That should be showing up on your formula chart, so hopefully you don't have to remember it too much. Hypotonic solutions, on the other hand, have less solute. There's less water molecules tied up, so there is going to be a greater water potential or a greater potential energy of that water to do work. So remember, water always moves from hypo to hypertonic solutions. I want you guys to memorize that. I know you could reason this out during the test, but during the test, you're going to be trying to remember a lot of different things, and I don't want you to have to sit there and think about the direction water's going to move. So memorize this fact. I also want you to memorize that, remember, hypotonic solutions have a high water potential, hypertonic solutions have a lower water potential, So water always moves from that hypotonic solution with a high water potential to a hypertonic solution with a low water potential. So if you memorize that, if you get a question that asks you, gives you some water potentials and asks you what direction that water is going to move, you have this memorized so you can just remember, oh, it's going to move from high to low water potential. And then just one more fact before we move on. Water potential is usually measured in units of pressure. And what you're going to find on the AP test is that it's measured in the unit of bars. Some of your water potential practice problems will have a different unit, which will be millimeters of mercury. A few might even have something in pascals, just because I got these water potential practice problems from a lot of sources, not just from AP test questions. But you don't need to know anything about the other units. You just really need to recognize bars. And that's going to be, when you see something measured in bars, chances are good it's going to be something about water potential. Now, let's talk equations, because yes, this is one of those topics where you're going to have to do math. There are two major equations to note. The simplest one is that the total water potential of something is going to equal the solute potential plus the pressure potential. Now, we've talked about water potential. Let's talk about solute potential. And sorry that laser pointer thing always shows up. So solute potential has to do with the amount of solute in something. As you add more solute, then the water potential is going to go lower. Now, solute potential, from everything I've ever seen, is always negative. And sorry, my tablet really does not like my hand resting on it, so it's doing weird things with the laser pointer and the cursor. This is going to become really important because pressure potential is the pressure from whatever container the solution is in. Now, if this container is a cell wall, then that's the pressure that's going to be exerted upon the solution in the cell by a cell wall. In an open container like a beaker, or you're having something described, usually it'll say it's in a beaker or an open container, then you have a very specific pressure potential. Your pressure potential is 0. So it's important also to remember the signs when you're doing water potential problems, because if you get that negative sign forgotten, you're going to get a completely wrong answer for a water potential practice problem. Then we have another equation, and this one is going to be slightly more complicated. So this is the equation to calculate solute potential. Let's look at each of these variables. I'm going to start with the easiest ones to identify, and that is concentration. And the unit for that is molar. Also, moles per liter. If you remember from chemistry, the unit molar is a compound unit, that's moles per liter. T is temperature in Kelvin. And a lot of times, since we tend to use Celsius as our generic standard temperature measurement for science problems, then you need to be able to convert from Celsius to Kelvin, and that's going to be your degrees Celsius plus 273. And don't worry, you don't have to memorize that. That is on your formula chart as well. There is also a constant on your formula chart, which is 0.0831 liter bars per mole times degree Kelvin. And yes, I realize that is a very complicated unit, but you'll see when we do some practice problems, that unit is like that just to help you cancel things out and get rid of units you don't want. And then finally, there is the ionization constant. And this has to do with the number of particles something will break into if it's dissolved in water. So anything that's covalently bound. The ionization constant is going to be 1. So something like a sucrose, sugars, amino acids, those are going to be examples of things that are going to have an ionization constant of 1. They don't separate, so they are only going to have their effect on the solute potential as a single particle. If you have something ionic, the ionization constant is going to be the number of ions. So something like NaCl, sodium chloride, is going to have an ionization constant of 2 because it breaks into 2 separate ions, each of which is going to have their own impact on the water potential. Something like CaCl2, calcium chloride, since it breaks into 3 separate ions, 1 calcium ion and 2 chloride ions, it's going to have an ionization constant of 3. I do want to point out that there are polyatomic ions, things like phosphates, that will probably not show up, but if you see something like that, this doesn't dissociate into a bunch of different, it doesn't dissociate into a phosphorus and 4 oxygens. It tends to stay together as a unit, so each of those polyatomic ions just adds 1 to your ionization constant. I also want to point out the negative sign in the solute potential. Remember that the signs are going to be very important on these questions. You don't want to forget the negative sign. All right, let's do some practice problems now. All right, so there are 3 sample problems in your water potential practice problems of different types that I wanted to go over. We're actually going to start with sample problem 2 because it is a simpler problem. So we have a plant cell, and keep in mind all these water potential problems will be in plant cells. The plant cell has a pressure potential of 2 bars, it has a solute potential of negative 3.5 bars, and we want to know what the resulting water potential is. If you haven't used this method in the past, I always use the guess method, which is something I use even subconsciously. You identify your given, what your unknown is, you figure out what equation is going to be best for it, you substitute, and then you solve. And I've been using this since I was y'all's age to solve math problems or science problems. So our given that they gave us is a pressure potential, which is 2 bars. We have a solute potential, which is negative 3.5 bars. And our unknown is our total water potential. If we look at our 2 equations we have only one that will work, that our total water potential is going to be our solute potential plus our pressure potential, which means it's going to be negative 3.5 bars plus 2 bars, which is going to be negative 1.5 bars. Now, if this was on the AP test, all you would need to do is have this. All the other stuff that I have is stuff that you could put on whatever scratch paper you have, but it does not need to be on your final answer because you don't need it. A few things I want to point out. You need to always include your setup and you need to include your units. If you don't do that and you're doing this on a free response question, you will lose potential credit. They want you to show, or we want you to show your setup to make sure that you know how to do the problem and you're not just able to guess a random number with, fidelity. So that's the simplest type of water potential problem. Let's look at the slightly more complicated one. So we're calculating the water potential of a solution with a specific concentration at a specific temperature in a beaker. So, few things. Let's do our given or our guess method. We're told that we have a concentration of 0.15 molar. I also want to use that other unit that I talked about, moles per liter, because it's going to become very important for canceling out units later. And as you can see, my cat is very invested in you knowing that. Then we are also told the temperature. The temperature is 20 degrees Celsius, but remember, we don't use Celsius for this equation or these equations. We need to add 273 to it. So our temperature is 293 degrees Kelvin. Now, you might think, that's the only information I'm given, but we're told that this is a sucrose solution, which should tell us an ionization constant, which is 1. If you look, and then we're also trying to find our unknown is our water potential, and they tell us it's in a beaker. That means that the pressure potential is going to be 0, which means that ultimately our water potential is going to be equal to our solute potential. So that tells me that we need to figure out our solute potential. So that means our equation is going to be solute potential equals negative ICRT. And remember, R is a constant, so that's always part of our given. So now we're going to substitute in our numbers. It's -1, never forget that negative sign, times 0.15 moles per liter, times 0.0831 liter bars per mole, times degree Kelvin, all times 293 degrees Kelvin. Now, a side note that I want to go over, and I'm going to write this in green so you don't think this needs to be on your actual paper. When we're multiplying fractions, we multiply across the top of a fraction and across the bottom of a fraction. And I'm going to work this out so you can see why we're canceling out units in this problem. So if I take all the units and ignore all the numbers, I have on the top of my fraction, I have moles times liters times bars times degrees Kelvin. On the bottom of my fraction, I have liters times moles times degrees Kelvin, and that's it. Remember, anything that's on the top of a fraction and on the bottom of a fraction cancel each other out. So I can cancel out my moles, my liters, and my degrees Kelvin. And then all I'm left with is my unit of bars, which is appropriate because this is a pressure potential. And that's going to give me negative, remember, don't forget that negative sign, 3.65 bars. Again, the stuff you need to include is this. Now, I have had different reports from different AP readers. Some say when I was your age, I was taught to put a box around my answers to help make it easier for the AP reader to find. Then as I started teaching, I got told that, no, you don't want to do that because if your answer is elsewhere and you put a box around an answer that's not the actual answer for your problem, you could risk losing points. I've never graded any of the problems with math on the AP biology exam. I usually tend to grade the graphing questions. So I can't verify that you do need to or don't need to draw a box around your answer. I kind of leave that up to you, whether you want to risk that. But as AP readers, we are told to read every single thing that you write. So if you don't put a box around your answer, we will still find your answer if it's there and it's correct. It just may take us a little longer to do so, but we are also constantly reminded that each of you is a student trying their best, and we are to search for points that we can give you. All right. Last sample problem is going to be number 3, and it may seem very simple at first, but I did want to go over something. So it's not going to be quite a math problem so much as it's a conceptual problem, and I like to visualize these things. So we have a solution inside a dialysis bag. So we did not get a chance to do my usual diffusion and osmosis labs just because of time. But usually what I do is I'd use dialysis tubing, which is kind of a a clear membrane that's semi-permeable. It allows water to pass, but not solutes. So you would basically have, it looks like a tied up kind of baggie. And it's sitting in a beaker in this case. They tell us what the solute potential is, the water potential is inside the bag. It's negative 6.25. Outside the bag, it's negative 3.25. And we want to know what direction the water is going to flow. So a few things to keep in mind. Remember, water goes from high water potential to low water potential. My bad, I was trying to draw a sigh. Which may seem pretty easy to do, but we are conditioned to think of positive numbers when we're looking at numbers and comparing values. So you might be tempted to think, oh, hey, that negative 6.25, well, 6.25 is a bigger number. That's got to be the higher water potential. But if you think about a number line, and this is kind of what I had to do in order to help my students out in the past, it just helps to kind of put this in perspective. If this was 0 on a number line, this was 1, 2, 3, 4, 5, 6 to the negative side. If this was negative 1, negative 3, negative 5, negative 3.25 would be around here. Negative 6.25 would be around here. And remember, the further to the left you go, the smaller the number. The further to the right you go, the larger the number. So technically, for negative numbers, the lower absolute value, so the low, like 3.25, 3 seems smaller than 6, that's actually the larger number or the higher number. So the higher number is negative 3.25, which is where water is going to start. The lower number is negative 6.25, which is where water is going to end up. So water is going to move into the bag. And that's your answer. Water moves into the bag. Keep that in mind when you're doing problems like this, especially if you're having issues with negative numbers. I know this was a longer video, but I like to try and explain things slowly. And honestly, if it got too much for you or too long for you, you could always watch it at double speed. Good luck on your water potential practice problems. Come to tutoring if you need help. And that's all for now.